Hello everyone. This short video is on distribution shape, relative location, and a measure called measure of covariation. In other words, looking at the relationship between two variables. Now, we are interested in the shape of a distribution because when we are doing descriptive statistics, we do want to know something about whether or not the distribution is right skewed, left skewed, or it is somewhat symmetrical. That just helps us find ways to describe the information that we have in front of us. A right skewed distribution means that it has this long tail to the right. Left skewed distribution, a long tail to the left. But when it's symmetrical, then of course the right and the left actually look very similar. So I'm going to go through the short PowerPoint presentation, and then I will demonstrate an example using Excel just to do some computation for me so that we could look at measures of relative location, that is what we call Z-scores, and then also computation on covariance. All right, so I'm just going to grab my notepad right here, and so switching over to my iPad, we will look at, as I mentioned, distribution shape, Z-scores, the empirical rule, and detecting outliers. So starting off with the shape of a distribution, there is a measure called skewness. If we say something is skewed, we're basically saying it is off center. So a symmetrical distribution would be one that has the mean and the median identical. So the bell-shaped curve, which is a very familiar curve, has the mean and the median identical. If we say now the distribution is skewed, then we're referring to it being off-center. But which way is it off-center? Is it off-center to the left or is it off-center to the right? So if it is right skewed, we will consider that to be off-center to the right. That means there are some large values in the distribution that are pulling the average up, above the median. It's pulling it towards the right. And if we say it is left skewed, then we're saying that there are some small values that are pulling the average down to the left of the median. So if we just look at the shapes that we have on this diagram, so an example of a left skewed distribution would be this one here. So this is a left skewed distribution. Left skewed. This is a right skewed distribution. Right skewed. And then this is symmetrical. All right. So there is a measure for skewness. It's a slightly complex measure, but if you have statistical software, you certainly can compute that rather easily. But it's just really important for us to be able to just say something about the shape of the distribution at this juncture. If you want to see what the formula looks like, the formula is n over n minus 1 times n minus 2 times the sum of x minus x bar cubed over s. All right. As a matter of fact, everything in that in here is actually cubed. All right. And so the shape of a right tail, if we get a positive skewness, it means that it is right skewed. And so we have these high values that is pulling the average. So the median might be here, and then the average gets pulled up away from it. And then this is negative skewness or left skewed distribution. So you can see the long tail this way, and the median might be here, but then the average may be here, mu, and the median, right? So it pulls it away to the left. And then of course here the mean and the median are the same. Skewness then in that case would be 0. So that's all we're going to do in terms of describing the distribution. If you had a sample problem and you asked to describe the data, you could look at the shape of the histogram and tell whether or not it is skewed just by eyeballing it for now. We're not actually going to compute the detailed measure. However, if you actually use analysis tool pack in Excel, which allows you to do some descriptive statistics, you can get a measure of the skewness if you wanted that. Z-scores. Z-scores, that's going to become very important to us over the next several weeks. So it's good to get an introduction to it at this point right now. So what is a Z-score? So whenever we have a distribution, we want to get a sense of where the values are relative to the average. And you may recall in calculating the standard deviation or the variance, we sort of measured the distance between the x values and the mean, if it was a sample, or the x values and the mean mu if it's a population. All right, we measured those distances, and then we computed a value which we call variance by sort of squaring these values, adding them up, and dividing by n if it was population. If it is sample, we calculated a sample standard deviation by taking x minus x bar. We square it, we add them up. We took n minus 1, we divided by n minus 1, sorry, that would have been the sample variance. If we want standard deviation, we just take the square root of the variance. Now, if we were comparing different distributions and we wanted to get a sense of the relative location of values away from the mean, what would be nice is if we could find a way to standardize those distances from the average. So I'm just going to give you sort of a plot and say, if this is my average, mu, and I have a value here, another value here, so let's call this x1, x2, x3, x4. All right, so I could measure the distances. If my data is in miles, then I have, distance in miles. If it's another distribution that happens to be weight, then my values will be kilograms, If it is time, it will be seconds. And so what if I was comparing two different distributions and I had two scores? So this one is in miles, and then what if this one is in kilograms? And I had a value here, let's just call it x1. I wanted to get a sense of the relative distance of this x1 from the mean. And if I wanted to compare it to the relative distance of this value here, x3, to this mean, I cannot just look at these two values and take the distance, because one will be in miles, that difference, and this other one is going to be in kilograms. And I can't really compare the two to say, oh, this value here is, its relative distance is a lot higher than the relative distance for x1, because miles could be very long, or very, compared to kilograms. One of the ways of sorting that out is to take a relative measure where we get rid of the units altogether. So what if we could express the distance between these two values in standard deviations? How many standard deviations is this value away from the mean? So what we do is we would actually calculate for the data the standard deviation, S or sigma, right? And then given the average, either sample average or population average, we could take any value, let's call it x, subtract the mean from it, and to express that distance in standard deviations, I will divide by the standard deviation, sigma. And that I call a z value. A z value. So it's a standardized value. We're standardizing the distances in standard deviations. So we're going to say, oh, this x is 2.3 standard deviations away from the mean. Another x could be 1 standard deviation away from the mean. Another x could be 5 standard deviations away from the mean, 3 standard deviations. So it's measuring how many standard deviations we are away from the mean, either sample mean or population mean. So we can, if we have population, calculate the average, not the average, sorry, the z-score. If we have the population, it would be x minus mu over sigma, but if we have a sample, we would still call it z, but we would say x minus x bar over s. All right, so that is population, and that is sample. So these are z-scores. And it's just a way of representing the distance between the average and the value. But one of the things that will become interesting to us is that the z-score will give us a sense of whether or not we have outliers. Because if we go back to the empirical rule says if we go plus or minus 3 standard deviations, right? So x bar plus 3s, or mu plus 3 sigma if it is population, or x bar minus 3s, or x bar minus, mu minus 3 sigma, then in that distance, 99.97% of all of the values that belong to that distribution should be in that range, right? Should be in that range between those two extremes. If that is the case, values that exist outside of that, values that we get over here or over here, are outliers. The extreme values. So we could use standard deviations to kind of measure for us whether a value is extreme or not. So if it is 3 or more standard deviations away, either plus 3 standard deviations or less than 3 standard deviations, 3 standard deviations away to the left, we will consider that value an outlier, an unusual value. And so we have this little rule where we could say if any value is greater than the mean by more than 3 standard deviations, or less than the mean by more than 3 standard deviations, is considered an outlier. So values beyond x bar plus 3s, or values beyond, in the negative side, x bar minus 3s are considered outliers. So we use 3 standard deviations. If the distance is greater than 3 standard deviations, right? If the absolute value of z, because sometimes it could be negative, is greater than 3 standard deviations, then we will consider this an outlier. All right. Now, our book also gives us another way of considering the outliers. If we had data like the first quartile, third quartile, median, and so on, right, which is basically the second quartile, we could find what we call the interquartile range, IQR, which is Q3 minus Q1. So using that interquartile range, what we will do is we'll determine an upper limit and a lower limit for our data. We'll determine an upper limit as follows, which is essentially, let me just get the right thing right here, Q3 plus 1.5 IQRs, and then a lower limit, which is Q1 minus 1.5 IQR. And so if a value x is less than the lower limit, we will consider it an outlier. If a value x is greater than the upper limit, we will also consider that an outlier. So that's another way, if we have quartiles, to determine whether or not the value in your distribution is an outlier. All right? I'm going to demonstrate an example with the Apple iPads question that we did earlier. This is just an example out of the text which shows standardized scores. So we had apartment rents. That's one of the earlier questions in the chapter. And essentially, we computed the sample mean, sample standard deviation, and for all the values, determine their standardized values, which is the Z values. And if we look at all of the data, the largest Z value is 2.27, smallest Z value is negative 1.20. None of those are 3 standard deviations or more away from the mean. So we would say that this data does not have any outliers in it, which is fine. Okay. Now there is an interesting rule called the empirical rule. That is a rule that we apply when we have data or a sample that we've collected. We have some raw values, and we want to determine whether or not that data might have come from a bell-shaped curve, a symmetrical distribution. In other words, if we look at the bell-shaped curve, if I have 50 values and I plot them, I may get a histogram, right? I may get a histogram. That might look something like this, and we say, oh, that looks like it comes from a bell-shaped curve. Well, we could test it empirically by taking the values from the data and then calculating 3 ranges from it. For the data, we would have to calculate X bar, which is the sample mean, and S, which is the sample standard deviation. You have to calculate those 2 values, and then we will determine 3 ranges. So we will determine X bar plus or minus 1 standard deviation, and then in that case 68% of the values in the sample that we have should be within the range, right? So 68% of the values approximately should be within the range. If I then went and took a range plus or minus 2 standard deviations, then that goes up to approximately 95.44%. And then if I go X bar plus or minus 3 standard deviations, it goes up to 99.74%. So that is why we use the 3 standard deviations as the limit to determine if something is an outlier, because if we were to take a range of plus or minus 3 standard deviations, we're saying 99.74% of all of the values should be in that range. So the chance of getting a value beyond that is very small. And so if it happens, if we find such a value, we will consider it an outlier. All right. So that we call that the empirical rule, because it helps us very quickly determine if there's a pretty good chance that the sample data that we have came from a bell-shaped curve, a symmetrical distribution where the mean is equal to the median. And later on we will come to know this in chapter 6 as the normal distribution, right? We'll come to know this as the normal distribution. So here's a summary of it right here. If the data came from a bell-shaped curve, so the empirical rule says if we go 1 standard deviation above and 1 standard deviation below, I'll put this part in red, right? So in that range is 68.2%, 0.26%. If we go 2 standard deviations, then we have to include this blue section right here on both sides. And now that makes the total and then I have to include the 68.26%, it now goes up to 95.44%, and then I could go 3 standard deviations. I'll include everything in green. That's 99.72. I said 74. Well, close enough. And in that case, let me just erase this. I didn't need that over here. In that case, so we have 99.72%. So there we go. So that's the empirical rule. Applying it is relatively easy. Just a matter of finding the sample mean, sample standard deviation, creating the ranges, and you physically count. So, in other words, if I had 100 values, I would for one standard deviation, so I would expect about 68, 69, 67 values to be in that range. And then when I take 2 standard deviations, if I count up how many of the 100 values are in the range, I should get about 95, 94, 96, somewhere in that range. It's not going to be dead on. And then if I went 3 standard deviations, then either all the 100 values or maybe 99 or 98 of those values would be in the range. Okay? And if we get that kind of consistency, we can say that we believe the data comes from a bell-shaped curve, a symmetrical distribution. And so that's the empirical rule for us. I've already talked a bit about outliers. So an outlier is an unusually small or unusually large value in the data set. So if we calculate z-scores and we are less than -3 or greater than +3, I use the absolute value instead. I said if the absolute value of z is greater than 3, then we'll consider it an outlier. And outliers could be caused either because somebody made a mistake, it was incorrectly recorded, or somehow the value was included and it should not have been included, or it could actually be a special case. So for example, if a company, an airline company right now, were to say, let us look at our travel data in the last 2 years up to this point. So let's just take a 2-year time window from, say, July of last year. Well, let's not, instead of 2 years, let's just use 1 year. July of last year to July of this year, or August of last year to August of this year. And we were to look at the data and we would plot it. Last year's values in terms of travel, the numbers I'm sure would be very high. And all of a sudden, because of COVID, there's been a huge drop in travel. I mean, companies like American Airlines laid off 19,000 workers, if not more. So what would happen is that you would have the actual travel numbers for like from March, April, May, June, July. These numbers are much smaller than the numbers in January or December of last year, November, and so forth. So what will happen is that you will find that the numbers during COVID might very well be outliers because they are more than 3 standard deviations away from the average travel. And the average travel numbers. And you say, well, why is there this unusual or unusually small set of values, and that is because of COVID. People were not traveling, right? And so there's often a reason behind an outlier, and we need to try to investigate what that particular reason is. This is just an example, and I'll show you here. And I want to move to measures of association. So to round out this chapter, so far we've been dealing with just one variable, whether or not it is wait times or it was the number of iPads that the various schools had in their districts and so on. But in this case here, what if we are interested in 2 variables and how they somehow relate? So for example, your miles per gallon that you get based on your speed at which you drive your car. Is there a relationship that if you drive faster, you perhaps get worse MPG performance in your car? Excuse me. If it gets colder during like winter months, do we see a drop in the consumption of ice cream, for example? Or do we see an increase in the sale of mittens? So is there some kind of association between these variables? If the prices of a house is related to interest rates for mortgages, if the interest rates for mortgages drop, will we see an increase in the number of housing purchases? Or will we see some kind of variation in the prices of the homes because there might be more demand? Sellers may want to raise the values of their houses, the prices of the houses a lot more. So in a case like that, there would be some kind of correlation or relationship between the two variables. So we measure that by using what we call correlation and covariance. The covariance essentially is just how the two values actually vary with each other. So our textbook gives us this formula as the formula for sample covariance and population covariance. But let me just give you a sort of a pictorial view of what I'm talking about, which is, let's use this guy right here. So if we have the two variables, and we said, for example, temperature and sale of mittens. The sale of mittens in dollars. Right? So of course, as the temperature increases, you expect sales to drop. So we should end up seeing some kind of relationship like this. So it's colder. If this is negative 20 degrees, maybe we're starting here, going up to 20 degrees, 25 degrees Celsius, we should start seeing a decline as the temperature goes up. So there is some relationship between those two, and that would be a negative relationship between those. But it would be nice to be able to measure the strength of that relationship, and that's where the covariance and correlation coefficient comes in. Now, covariance is kind of the equivalent of how we computed the variance of single variables, like when we were just doing time or weight or whatever. A single variable, we just said what's the variance of the data that we had, what's the standard deviation of the data that we had. Well, in this case, if we're talking about sales and temperature, we refer to it as covariance because they are varying together. Covariance. So one depends on the other. And the sign tells us which way they're varying. That if temperature goes up, sales of mitten goes down. So that means our covariance will be negative. If interest rate goes up, then the number of houses that are actually sold goes down, then the relationship is actually negative. But the sale of ice cream to temperature, instead of mittens, as it gets hotter, we want more ice cream. As it gets hotter, we want more water. So maybe the sale of water to temperature, we might see some kind of positive correlation in that case. So how do we measure it? So the first thing is to get covariance. And the covariance is given by, and remember I gave you a shortcut formula, so I'm going to give you that shortcut formula. Your book will give you this instead. First, let me show you what your book gives you. The book will give you, and I'm going to do sample covariance because very rarely do we have population. But if we have population, we know what to do. But I'm going to give you sample variance. So we will take x minus x bar times y minus y bar, and I'll explain what the y and the x refer to in this case, and divided by n minus 1. So it kind of looks like when we did x minus x bar squared over n minus 1, except that instead of just having one variable, we now have two, x and y. So we usually refer to x as the independent variable, and y as the dependent variable. All right. So, for example, the sale of ice cream is dependent on the temperature. So X would be independent, which is the temperature, and Y would be the sales. So Y would be sales, X would be temperature. So we should always know which one is dependent, which one is independent of each other. So sales is dependent on temperature. Your MPG performance, your miles per gallon performance, right, is dependent on the speed at which you drive. So the speed would be X, the MPG performance would be Y. So that's covariance. Now I want to give you a shortcut formula, but I would strongly suggest that you can use Excel once you understand the problem. It doesn't matter to me too much whether or not you use this long formula to calculate it, or if you could use Excel, put all the data in Excel and do the computation in Excel itself. So there's a shortcut formula for this. Covariance X comma Y is X times Y, X times the sum of Y, all right? And we divide this by N, divide the whole thing by N minus 1. So what have I done? I've simply replaced this term by this term. In much the same way I gave you a shortcut formula for the variance of X by giving you X S squared was equal to the sum of X squared, sum of X, all squared over N divided by N minus 1. Same way I gave you that formula. All I'm doing now is instead of X squared, I have replaced X squared by X times Y. And instead of the sum of X squared, then I would take this and use one of the sum of X, and then the other one is the sum of Y. And that's how we end up getting this formula. So they're very similar. It's just that we are changing, instead of X times X, we're going X times Y. Instead of sum of X times sum of X, to get the sum of X squared, we're getting sum of X times sum of Y. So very similar. So that is how we would calculate covariance. So now that becomes covariance of X and Y once I changed it. Now to get the correlation coefficient, which measures for us the strength of the linear relationship or the association between those two. So we have a term called correlation coefficient. So that correlation coefficient, we could denote it by rho for population, or R for sample. And then rho or R, whichever one you use, varies between -1 and +1. The closer you are to 1, the stronger the association, linear association. The further closer you are to 0, the smaller or less the association. To calculate rho or R, it all depends on if we have sample versus a population, is really given by the following formula: the covariance of X, Y, divided by the square root of the variances of X times the variance of X times the variance Y, or I could put it as standard deviation. Standard deviation. If I could use shorthand, the standard deviation of X times the standard deviation of Y. When we're putting that down, in symbols, Your book writes it this way for population. It shows a sigma xy as covariance, and then it shows you sigma x times sigma y. That's for population. If we're doing S sample, SXY, SX times SY. So in other words, the sample covariance, and that's the sample standard deviation of X, sample standard deviation of Y. And that's the way in which you would do that. To give you what the formula should look like, if you're doing a shortcut formula, I'm going to give you my shortcut formula. And that's the formula that I have in the that's the formula I have on the formula sheet. So I'd like you to pay attention to that. Try to find some space for this guy. It would be R or rho would be the following. It would be sum of x, y, sum of x times sum of y, put it in brackets, over n, divided by the square root of sum of x squared, sum of x over n, sum of y squared, sum of y all squared over n. It looks complicated, but essentially what we're doing is we're just taking the numerators from the various formulas. This numerator comes from the covariance formula. This numerator will come from the formula if we were calculating the standard deviation of y, and or the variance of y. And this numerator will come from the formula if we were calculating the variance of x. That's all. All right? So if you just calculate those separately, it's really not that hard. It looks complicated, but it's really not that complicated. One of the best ways to set up this problem when you are doing it is to create a table with all of your data. I'll just show you what I mean, and then you will find it relatively easy to do. So x will be your values of x, y, x times y. Then we go x squared and y squared. All right? Yeah, that's fine. I should have said x, y, x squared, y squared, and then x times y, but it doesn't matter. And so with these values here, so for example, if this is 2, and this is 4, x times, then that's 8, 2 2's, I miss a column here. I have an empty column, but don't worry about that. 2 squared is 4, and then 4 4's are 16. And when we calculate all of our values, then you will have, in this case here, sum of x, you'll have the sum of y, you'll have the sum of x times y, you'll have the sum of x squared, you'll have the sum of y squared. And these are the values that you will need to put into these formulas. So just put everything in a table, put it in Excel, add up, do the manipulations, add them up, and then simply compute those values. And that would be it. All right. So just finishing off, SSXY is the covariance, sample covariance of two variables that we believe have an association. If this is sample, we use this. If it's population, we use that. But very rarely do we have a population. And then we could see here that the correlation coefficient, which is a measure of the linear association between those two variables, to what extent there's a straight line relationship. This is the covariance of xy, but these two here are sample standard deviations, and that's population in this case. Generally, I don't really like the notation too much because the SXY is really at the variance level, and over here SS and SY are standard deviations. So remember, variance is order 2, standard deviations is order 1, but they still use S in both cases right there, which I find sometimes can be a little bit confusing for some people. But anyway, as long as you know that the numerator there is the covariance, and then the denominators are standard deviations. If you wanted everything to look like variances, then you could alternatively write sxy over the square root of s squared x times s squared y. So that's a variance, that's a variance, that's a variance, covariance. But remember, we take the square root of those to give us standard deviations, right? Does it matter? Not really. It's just whatever that you can work with that helps you to remember better, that's fine. So you certainly can go with that. In fact, in the shortcut formula that I gave you, which if I go back here, that shortcut formula is actually derived from what I just showed you, which is looking at the covariance, or sxy, and taking the square root of the variance. So that formula is actually derived from that, right? That's why you have these terms in here, because these are the numerators when you're calculating variances and so on. Okay, so that's, I think, enough to get us going. And the points that I made earlier, closer you are to -1 or +1, the stronger the relationship, the linear relationship. -1 is a negative linear relationship, +1, positive linear relationship. As you get closer to 0, the presence of a linear relationship is less intense. And we could do computations to get us to take a look at this. In a separate short video, I will actually just demonstrate these two problems for you, finding z-scores and finding correlation coefficient. Okay, so see you in the next video.